Hello, welcome to Math 251 Calculus 1 here at Cañada College. My name is Lapuz and I'm the instructor for the course. In this video, we will take a peek at section 3.1. Section 3.1 talks about defining the derivative. So we're going to go back to the tangent line problem, and then we're also going to take a look at this from the velocity point of view. So in our problem, if you remember, we start off with a difference quotient to find the slope of the secant line. And so the slope of the secant line will be given by the difference of the y values, the f of x minus f of a, divided by the difference of the x values, and that would be x minus a. So this is known as a difference quotient. Now if we replace x minus a with h, then we can also replace x with a plus h, and so we can also rewrite our the same difference quotient using f of a plus h minus f of a divided by h. Now this is still going to give us the slope of the secant line, and if you remember the slope of the secant line, we take limits as the values get closer and closer to our a value to eventually get our tangent line. So in this picture we have secant lines, and they're showing the same graph, but they have different labels on them because for one of them they are using the first difference quotient, for the other one they're using the second difference quotient. And so in either case, regardless of what difference quotient you use, you're eventually going to get the slope of the tangent line, and the tangent line is going to be the line that best approximates the function at a particular point. And so formally that will be the definition of the tangent line, and since we are in fact relating the tangent line with the derivative, this will be our formal definition for the derivative. So the derivative will be defined, the derivative at a particular value a will be defined by either this the first difference quotient, the limit of the first difference quotient, or the limit of the second difference quotient. So both of these will give you the same result, and I'd have to say, like, the first difference quotient is a little bit simpler to understand, but the second difference quotient will become important for us in the next section when we actually want to define, not just find the slope at one particular point, but to actually define the derivative as a function. All right, so we're also going to immerse ourselves with a velocity problem, and it's just like the tangent line problem. So you're going to be given an average velocity, so to speak. So we can say the average velocity is going to be the difference quotient between some t value and some a value, and that's divided by t minus a. So it's going to be the difference in the s functions, or the y values, or whatever the position functions are, divided by the difference in time. So we can think about this as ds dt, or the change in s over the change in t. To find the instantaneous velocity, that would be the derivative. So instantaneous velocity is usually denoted by little v. So v of a is equal to the derivative of your position function, if your position function is s, and that's going to be the same difference quotient with a limit as t approaches a. Okay, so that is our basic rundown of section 3.1. We're doing the tangent line problem, we're doing the velocity problem, and then we're inching our way to using the definition of the derivative to help us find derivatives, and then derivatives in general. And this is our first step. All right, I hope that helps.